All right, welcome back. We're going to go through our next section here. This is called curve sketching. So we're going to put together the differentiation that we've done with exponents and logs in this section, and we're going to combine that with everything that we've already learned about curve sketching in previous sections. And so just as a reminder, all of the things that we look for: domain first, and then looking at your intercepts. Symmetry is when you take f of negative x, can you find that it's an even or an odd function? And that'll tell us something about what it looks like. Asymptotes, both vertical and horizontal. If we have a vertical asymptote, looking at both from the left and right, horizontal asymptotes going to positive infinity or negative infinity for x. First derivative and then intervals of increasing and decreasing, maximums, minimums, second derivative, then concavity, and then putting it all together as a graph. So we're going to go through this with y is equal to x times e to the x. Okay, so to answer each of these questions individually, x e to the x, let's start with part A is domain. And x times e to the x is defined for all values of x. You can always plug a number in for x, and so there's your domain. Intercepts, if we look at, if I say that y is equal to f of x, and now I look at when I take x as 0, then this becomes 0 times e to the 0, which is just 0. So therefore, 0, 0 is both your y-intercept and an x-intercept. There isn't another value of x that makes this 0, because e to the x is always positive for any values of x, and we're going to use that fact a few times here. So 0, 0 is our x and y-intercept. Looking at part C, if we have symmetry, remember that what we take is we take f at negative x. And for it to be an even function, just to remind you, for an even function, if this is, simplify it and show that it's equal to f of x, then it's even. If we can show that it's equal to the negative of f of x, then it's an odd function. And so what we're going to do is we're going to chase down what negative x ends up being equal to, and we'll see where that takes us. All right, so f of x is equal to negative x e to the negative x. And therefore, there's no symmetry with this. There's nothing really we can do with this to make it look like either. We can't, if we factor out this negative, then this ends up being, well, I guess it is already factored out. It's the negative of this, but that's not what f of x is. So therefore, by this, no symmetry on this. If we look at asymptotes, we have no vertical asymptotes. Because it is always defined for any value of x. If we look at horizontal asymptotes, what happens? And the limit x goes to infinity of x times e to the x is positive infinity. Right? We plug in larger values for x, and both of those factors go to positive infinity. So therefore, no horizontal asymptote going off to the right. If we go off to the left, the limit as x goes to negative infinity. This ends up being a little different. X times e to the x. And what happens with this? This is a little interesting in that we don't quite know, because this factor here is going to negative infinity, and this factor here, when e to the x, when x is going to negative infinity, you have e to this larger and larger negative number. And when that happens, this is going to 0. So this is going to negative infinity times 0. Now, this is unclear of what this ends up being then. Therefore, we have to kind of think of this. We could do a numerical analysis and substitute some large values, large negative numbers for x. So negative 100 times e to the negative 100. And we can see what's happening with this. What we'll do right now in this course is we're going to reason that what's happening faster, which is the more powerful term. And what it ends up being is this ends up being equal to 0, because this ends up being e to the x ends up being it ends up being a bigger force. E to the x goes to 0 much faster than x is going to negative infinity. And so that's kind of the reasoning at this point that we have to use with this. So either reasoning like that or numerical analysis with that. When you get into calculus in university, they'll show you something that is called L'Hopital's rule. This ends up being a very powerful tool in how we can interpret limits of functions. And so we will use L'Hopital's rule a fair amount in first year calculus, but it ends up being a pretty powerful tool. And we would normally, that's how we would figure out that this ends up being equal to 0. But for now, just maybe a table of values and numerical analysis, or just reasoning about what's happening in here. All right, next part, E. So we have E, this was D, I think. That's the world's ugliest D, sorry about that. E, here we go. So we need critical numbers. So let's take our first derivative. If y is equal to x, then y prime will equal this. We take first derivative of x is just 1 times e to the x. I'm going to add that to x times the derivative of e to the x, which as we saw before is just e to the x. Common factor this. E to the x, 1 plus x. If this is equal to 0, numbers, when x is equal to negative 1. E to the x as itself will never equal 0. It's an exponential. It has a horizontal asymptote. So 1 plus x makes this 0 when x is equal to negative 1. If we are looking at our number line, then what happens? Negative 1, as e to the x is always positive, 1 plus a number that's less than negative 1, such as negative 2, will be negative, and then a value greater than negative 1, such as 0, will make this positive, which tells us that this function is decreasing to negative 1, and then it's increasing afterwards. State that decreasing on negative infinity, negative 1, it's increasing on negative 1, sorry. Therefore, part F, we have a relative minimum because it's decreasing and then increasing. 1. Here, so we had a relative minimum at x equals negative 1. So therefore, f at negative 1, we plug this back into negative 1, 1. 1 comma negative 1 over e is your minimum. Second derivative. So if y prime was e to the x times 1 plus x, then second derivative will be, take the derivative of b to the x, product rule, and so times 1 plus x stays the same, times the derivative of 1 plus x, which is just 1. And this ends up being equal to e to the x 1 plus x 1 e to the x x plus 2. There's our second derivative. And I'm going to run out of room, so I'm just going to write this over here. That when this is equal to 0, then our second derivative, we have a possible point of inflection at negative 2. And when x is less than negative 2, this ends up being negative. When x is greater than negative 2, this ends up being positive. So this is concave down, and this is concave up. Concave down, negative infinity to negative 2. Concave up from negative 2 to infinity. And therefore, we have a point of inflection. X is negative 2. We run that through our original f at negative 2, and this ends up being equal to negative 2 times e to the negative 2 is negative 2 over e squared. There's my point of inflection. All right, we'll put all that together in a graph. We know that we have this minimum at negative 1. What did we say? Negative 1 comma negative 1 over e. If we want to decimalize that, just so we can have our head around that, where that would go as a graph, this ends up being negative 1 divided by e. It's negative 0.37 approximately. If we have this other point, negative 2, for our point of inflection, while we've got our calculators out, negative 2 divided by e squared is approximately negative 2 comma negative 0.27. Just so we can have our head around how this is going to go for a graph. Probably a good idea when we're starting to create our graph, just to make our axes and see where this is going to go. We don't need much below the x-axis, so let's draw our axis down here. We know that 0, 0 is a point. We know at negative 1 and negative 2, we've got points of inflection and minimum. We could make this, there's negative 1 down there. So we have this minimum at negative 1, and then negative 0.37. And we have a point of inflection at negative 2 comma negative 0.27. We know that we have a horizontal asymptote as we go to the left. So this is going to continue in this direction. Let's maybe make this in a different color. So we have this horizontal asymptote here. This is concave down until it gets to this point, and now it inflects to be concave up. We have a minimum at -1, and we go through the point 0, 0. As x goes to infinity, y goes to infinity. So this will all be concave up through this minimum, and it looks like we have horizontal asymptote, even though it is only when x goes to negative infinity, it is still our horizontal asymptote, y equals 0. This is -1, comma -1 over e, and this is the point -2 over e squared. And that's what this graph looks like. So one tool that you can use when you're graphing, when you're trying to sketch stuff, I think that it makes sense to use it once you're done. Once you've put all these pieces together, then you can check your work. If you're stuck, you can kind of also use this at times, and it ends up being kind of a powerful tool. I'm just going to open up another browser window here. And I'm going to go to a website called, I'm going to Google GeoGebra. And when we do this, here, geogebra.org, if I'm going to go to this website quickly, it says start graphing. Let's go to the graphing calculator. It ends up being kind of a better graphing calculator than your TI or your Casio. It ends up being a fairly easy to use interface on here. Sometimes typing math in, whether it's an email or anything else, ends up being kind of a bit of a chore, and it looks really chunky and it's hard to use. But in this graphing calculator, it's really, you've got some good math tools down below here. So let's go to type this in. I'm going to type in y equals, and I'm going to type this in. And as I start typing it in, it'll start to graph it. I type in an x. We can use this x down here. Notice that we have a button for e. So let's just even type in. You can push that, or you can even just call it e. It knows the difference between those. And so right now it's just, actually, no, that might be wrong. It might require us to use this E. There it is. Yeah. So let's use this. Let's click this button E. Now we want an exponent, so we're going to use this, and then we're going to raise it to a 2. Either type in a 2 or click it in here. When you hit enter, no, delete. It's not e to the 2. It's e to the, aha, sorry about that. There we go. E to the x. And as soon as I hit enter, it will now graph that for us. And it ends up being just kind of like what we sketched it. We see the asymptote there. If you click on this graph, if you click on this point, it'll give you that extreme. It'll say -1, -0.37. It'll tell you your root or your y-intercept. Well, it's both, is at 0, 0. I don't know if it tells us this inflection point here if we click on it, but that's okay. Anyway, it ends up being a pretty powerful tool, just kind of confirming what you're supposed to be doing with this. And so you can look at this and we can see, okay, I can see how it's concave down till it gets to here. And we can zoom in on this a bit and we can start to see how the concavity changes right about there at -2. It's concave down to -2, and then from -2 on, it's concave up. Anyway, kind of a powerful tool that you might want to use, especially when you're doing curve sketching, just to kind of confirm that you're on the right path. All right, good luck with this today, and we will see you again.